Welcome everyone. Morning, afternoon, or evening, depending on where you are in the world. Glad you could join us. And I'm glad that you remembered the change of day of the week for the talk. So it gives me great pleasure to introduce our speaker today, Dr. Stéphane Mounier, who is from the University of Toulon. And I should just start by acknowledging that Toulon University has recently become a member of the IIES, and so we're very pleased about that, and equally pleased to have you speak with us today, Stéphane. So Stéphane is a researcher at the Mediterranean Institute of Oceanography at the university. He obtained his PhD on the flux and characterization of organic matter in the Amazon River at the University of Paris 6. And he works on the spectroscopy of organic matter and its interaction with metals in various environments, such as soils, lakes, seawater, pore water, sediments, and solids, using PARAFAC decomposition. And I have to confess, Stéphane, I'm not sure I know what that is. So maybe at some point you'll let me know. And his latest work is focusing on mangrove organic matter and its fluorescence characterization. So welcome, Stéphane. And you can go ahead and start sharing your screen.
Okay. Let me share. Up. So thank you, Doug, for this introduction. This presentation is about carbon dynamics and contaminant in mangrove ecosystem. And more specifically, we will focus on what happened in mangrove sediment and the role of organic matter in contamination or metallic contamination. Before, for me, it's necessary to define what we are talking about. Is for metals, there is no ambiguity. For organic matter, there is several words. We talk about carbon, we talk about organic carbon. And it is important to remind what compartment we are talking about. So what carbon are we interested in? In fact, we saw in the literature a lot of expression, blue carbon, stock of carbon, carbon dioxide, etc. And also organic matter, labile, etc., refractory organic matter. But what is this carbon is? So carbon is just a general point of view. Carbon there is two forms. There is the inorganic carbon, the oxidized form, and the most common form are carbon dioxide and carbonates. And these two forms are in relation between several compartments, because the carbon dioxide can associate with water to make carbonic acids. And this make a relation with atmosphere, because when you have more pressure of carbon dioxide, you have more acidic carbonic acid in the water. And if there is a variation of pH, or if you reach some basic pH, you can see the apparition of carbonate. And this carbonate can, in some condition, concentration or pressure, can precipitate in solids. So in fact, the inorganic carbon is principally gaseous, liquid, or in solution and solids. And there is also two other forms that are less important, is graphite and diamond. Okay, but generally, we also discuss about organic matter. So the organic matter is reduced carbon, in fact, and is based on the name that we have a skeleton with carbon. Okay, so it contains organic molecules, simples from urea or some very simple molecules, but it can be a little by little more complex, like oil or proteins, until lignin or big proteins that we can call biopolymers. This part of biopolymers is about 20 to 30% of the organic matter in the environment. And all these big molecules or biomolecules are degraded by biotic or abiotic processes, and they give a lot of thousands of molecules that have several structures, and we call generally this this part, this undefined pool of organic matter, geopolymers. Also, we can add in this pool of organic matter all the molecules that we made, the human made, like plastics, chemicals, etc., because they are, by definition, organic matters, because their skeleton is made with carbon. So when we talk about organic matter, or when we talk carbon, we talk about one of these compartments, or the organic, or the inorganic, or about organic matter, or about carbon. But all these pools are linked. What is the distribution, in fact, in the Earth? 99% of the carbon on the Earth is in the rocks, in fact. You can see that most of the carbon is in the sediments, in the crustal Earth. And there is, if we take apart these sediments, we have a small part that is in the water, seawater and ocean. But even in this compartment, ocean, we have most of the carbon. I don't know if you see my mouse, but most of the carbon is inorganic one, carbonate, and a little part is organic. And this part of organic carbon is more or less the same than the biomass that can be in river, on air, on soils. So only finally 1% or less than 1% of the carbon on the Earth is organic matter. Why it is important finally to care about this small part? It's because, as you know, it is in relation with several reservoirs. We have the atmosphere, we have the hydrosphere, ocean and river, and we have the soils, pedosphere, and we have the lithosphere, which are the biggest reservoir. And in fact, between these reservoirs, there is not the same kinetics. So when we increase the CO2 in the atmosphere, it takes a longer time to go in the hydrosphere and pedosphere, and a longer time to go in the lithosphere. And it's why this link is very important. We try to now diminish the production of CO2 and to increase also this transfer from the atmosphere to the pedosphere or to the hydrosphere. In fact, we try to trap the carbon, or we want to trap. So, this carbon in soils and hydrosphere is not homogeneous. We can see that if we take into account the biomass distribution, the productivity is not the same around the Earth, and principally depend on the latitude. So in North latitude, we have less production, and the maximum of biomass production is near the tropical zone in the south. This is probably due to the temperature. Most temperature, higher increase of plants. But for the soils, it's more or less the contrary. Because if you look at the distribution of carbon in soils, we have in the north higher content of carbon or organic matter in the soils, you can see here, and lesser in the south. This also is due to probably the temperature, because if you have higher temperature, you have higher biological activity in the soils, and you have a higher mineralization of organic matter. But what about mangroves? Because we want to talk about mangroves. So mangroves, they are important because they represent 0.5% of the coastline, but 10% of the carbon export to the ocean. When we talk about carbon export, it's organic carbon export. And also, this small part of the surface, they are 3 to 5 times high efficient to stock carbon in the biomass. So it's why we are interested in mangrove, and we want to know how it works inside these ecosystems. Also, if we talk about biomass, it's not really the same thing that if we talk about content, in fact. Because if you look at this map, we can see that there is carbon content, a difference in carbon content depending on the region. The Indonesian and North American region zones seems to be more productive here and here. And this is a prediction for the 1 top meter of soils mangroves, in fact. So the average, more or less, if you take this around the world, it's around 370 megagram of carbon by hectare. But this evaluation is probably underestimated because there is a lack of study in certain regions, particularly in Africa. And also, we take only in this prediction only in account the first 1 meters of sediments of soils. But more or less, we can see that the central Indo-Pacific region is more efficient to burial carbon, and also more or less tropical Atlantic. Also, it's difficult to study organic matter in mangrove because there is a difference between the morphology of carbon. On this same work from Sarka, we can see that depending on the sorry, it's represent. I forget to say that it represents only 1 to 4% of the organic matter carbon stock. But export, sorry. Depending on the typology or morphology of the mangrove, you have also different variability of carbon burial. So depending on the mangrove, you can expect some difference, and it's very hard to have a global or general point of view of the functionment in the stock of carbon. So more or less, we can say that whatever the system, we can expect 2,000 to 4,000 grams of organic carbon by square meter by year concerning the stocks. And also, it's not only the morphology or the superficie of the mangrove, it's also the age of the mangrove, because we can see on this work that depending on the age of the forest, either it's forest, there is a difference in the capture of the carbon in the system. So at the beginning of the increasing of the forest is not really efficient. The maximum of efficiency is between 10 and 20, and after it decreases, and after 40, it's a little bit more complicated to have a trend. Okay. This was a general introduction for the organic matter, carbon, and we saw that we can expect a very large structure and large functionment for organic matter. But what is the dynamic of organic matter and metals in mangrove systems? So, estuarine mangroves received, in fact, it's known the river inputs from the land, okay? This matter or this organic carbon, but also inorganic, but this carbon is alloctonous, and it integrates the contamination and the erosion of all the watershed. These inputs encounter the seawater and sulfur tidal events, and this mixing process modified the geochemistry of the system, salinity, temperature, oxygen, etc., but also the physical system with velocity and density. And part of this dissolved organic matter settles on the surface of the sediments, and one part go through directly in the open ocean, and another part go into flocculation and aliments the surface of the sediment. On this surface, there will appear high activity of microorganisms, and there will have some depletion of oxygen, and it will appear some modification in the speciation of the metal of the carbon inside the sediment. Some layers will appear. And for the metal, it's the same thing. Dissolved metal go with the organic matter and go to flocculate. Part of this metal will associate to the flocculation with the absorption, and for this, the principal drivers are the solubility of some elements, for example, chloride or some species for chloride or carbonate, but also the adsorption on surface. And this surface can be, this surface can be a mineral surface with clay and silt, etc., but also the new formed surface by the organic matter that suffer flocculation flocculation. Concerning the particulate inputs, it's the same thing. We have the same systems, but we can add in the particulate some autochthonous inputs from biomass and from atmospheric depositions. They add this on the surface, and we have some fresh organic matter, and this will suffer a diagenesis process and intertidal exchange with seawater. What is diagenesis, in fact? Oh no, sorry, it's not what is. What is the stock of metals and carbons in the mangrove? We can separate two, more or less. We have the overground carbon and the underground carbon in the biomass and in the sediments, even if we can consider that the roots of the mangrove inside the sediments make parts of the biomass compartment. So these compartments, we can see here that metals are not distributed in the same compartment in the biomass. This is a work from Ramos. We can see that, for example, for iron, we have most iron below ground roots, and for zinc, nickel, and chromium, it's in trunk, and for aluminum and copper, and for zinc, nickel, and I missed the line, but it is in trunk and in it is in the battleground. It is in roots for the nickel, aluminum, and copper, and it is in trunk for zinc, nickel, and chromium. And for zinc, it's more or less same distribution between branches and below ground. What it makes this difference is probably due to the difference of chemical species that are present in the sediments. And we will see that these species come from the speciation of metals and the interaction probably with organic matter and some mineral ligands in the sediments. On this work, Ramos tried to make some balance in biomass. So he estimated that from the litter fall, there is some flux of metals here that come on the reservoir of biomass, and one part is exported by the biomass. And we can see that, except for cadmium and zinc, the balance is negative. It means that the mangroves are sink of metals, and the stock of metals in biomass should probably increase. But in sediments, there is another story. In sediments, there is a story between clay, organic matter, and metals. At the surface, there is fine particles that settled on the surface, and these fine particles offer a very high specific surface. And this very high specific surface allow the association of this clay the clay with organic matter. We can see here that if we take a profile of sediments, we have at the surface more clay and more carbon. They are in fact associated. And this association of clay and organic matter also induced association with metals. If you look at this work, we can see that when it's the same site, but when there is less clay, there is less metals. And when there is high content of clay or organic matter, there is higher concentration of metals. It means that between clay, organic matter, and metals, there is an association. And generally, we can say that we have a concentration that go increasing from sea toward land. And the more the site is exposed to high energy, like wave and perturbation, the less we have clay and the less we have metals and carbon. So metals and carbon are associated in this type of consideration. And if we have some protection, we have higher fine particles, and we having higher fine particles, we have higher association to metals. This means that the sediments of mangroves can be used, and they are used to measure the activity of the basin. This can be seen on this work from Hassan here. We have the metal content in two sediment surface, and they are measured between 2008 and 2015. And we can see that for the Guangdong province between 2008 and 2015, we have an increase of chromium, arsenic, and lead. Concerning the Guangxi province, we have a decrease of lead and zinc and a little increase in chromium. This means that the sediments are register the activity, because on the Guangdong province, between these two dates, it was an increase of economic activity. So when the economic activity arrives, there is an increase of contents. And for the Guangxi, it's a change of activity. It means that they pass from industrial to tourism, and there was a registration of what's happened in the watershed. It means also that the sediment of mangroves are very reactive. So they change in very few time, and they integrate the contamination, and they keep this memory inside their metal contents. Anyway, it's not only the total concentration of metal that is important in sediment, it's also what's happened in the species in the sediment. And to understand what's happened to metals inside sediment, we need to go a little bit more in the diagenesis process. So on the left graph, we have a sediment, and on the right it's another. But on the left, we can see that there is some heterogeneity in the sediment, and the brown mark are in fact oxidate one. And the oxygen was brought by the roots here, and it means that on this part there is oxygen. And the roots bring the oxygen to this zone. But when you see at the black one, in fact, there is a depletion of oxygen. This means that depending on the bioturbação and the zone and the sediment, it could be very difficult to have something homogeneous. On the left picture, you can see that it's very hard to make something global, because there is small zone of different environment or chemical environment. But on the left, it's more homogeneous, and you have, I don't know if it is well defined on my picture, but on the bottom of this sediment, there is black color here, and it is the reductive zones. So what is the diagenesis process? In fact, so I told you that surface of sediment are alimented by fresh organic matter from inputs of river, particulate, dissolved that flocculate, and also some biomass that arrived on this surface. Rapidly on the top of the sediment, the oxygen is consumed and cause some depletion, turning the environment anoxic. But if there is no more oxygen, bacteria will use other oxidant. It's not the same bacteria. There is a change in the bacteria between the surface to the bottom, but some bacteria are able to take oxygen from nitrates, and so you will have the use of the nitrates on these sediments, and they will consume these nitrates. After the consume of the nitrate, they will use the manganese oxide and the iron oxides until the sulfates. And the sulfate, the use of sulfate for respiration, in fact, cause some precipitation, or by the help of some bacteria, cause the apparition of pyrite, that is solids. And this pyrite can co-precipitate some metals. And at the end, at the bottom of the sediment, and not always, but it can occur, you can have some methanogenesis, the production of methane. it is the organic matter that dismutes, and one part is used for respiration, and one part is used for biomass production. So all these layers are in equilibrium normally. I suppressed some slides that show that this equilibrium is very rapid, in fact, and can move in the hour. Depending on the condition of fresh organic matter or fresh oxygen of tidal frequency, this layer will move rapidly. If there is no change, the only production of or the only exportation of metals or the only exportation will be the advective transportation or advective transfer from the bottom to the surface. But in mangrove, it's always modified, and there is always a modification. But once we talk about this organic matter as a fuel for diagenesis, what is in fact the interaction between organic matter and metals? We only discuss about reduction, oxic, but we didn't talk about interaction. So of course, the organic matter is not only the fuel for diagenesis. It is observed in most of mangroves in the world that metals exportation is associated to organic matter exportation. In this work from Lu, we can see that they associate the organic matter export to the metallic export. Here it's for manganese and cobalt. And generally, in the literature, there is no study of the mechanism. It's only there is a correlation, and this correlation induced some complexation of metal. But it's not clear, because it's not because there is correlation that there is relation. So we need to investigate a little bit more what is the speciation of metal and what is complexation in terms of chemistry. So if we take this scheme, it is the scheme of metal speciation. When there is a metal, a cation in solution, we have several compartments. We can have several compartments in equilibrium. One part is the solid part. In fact, what we call solid part is not included in mineral lattice, but it just complexation or adsorption on surface solids. So this part is called more or less solid or inorganic or particulate metals, and it can be associated with functions that are organic or that are inorganic. It's difficult to make the difference. Another part of the speciation is the complex one. So this part is the association by complexation of metals with several ligands. Most of the ligands could be inorganic, like chlorate, like sulfate, etc., or hydroxide. And one part is organic. It could be simple molecules like exudates, or it can be organic matter. And what is organic matter is complicated to say. So we can talk about humic substance for the moment, but these organic matter are organic ligands. And there is several forms of metals. And the most little part is the free ion. The free ion of metals is, in fact, the smallest part of the system. Generally, when you make some modelization, it represents less than 1% of the total metal concentration. And what is interesting here is that generally this free metal or this free ion is considered as the toxic species, because this is the species that can enter in the cell wall and make some damage in the biota. But it's not always the case. It depends on the metals. If we take, for example, mercury or arsenite, is not really the free metal, the free ions that is toxic, but the complex form. So we have to take into account that most of the metals are toxic are toxic in the free ion form, but some are, at the contrary, non-toxic. So when we talk about this, toxicity is the free ion, but we can also talk about metals for translocation, because the metal that is in roots and leaf, etc., is not really a speciation, but one part is related to this available metal. And the exportation of metal is related to the several forms, in fact. Mostly complex and free ion, because it is water that go through the mangroves, but also part of the particles, because it depends on the strength of erosion of the particles, and also in biomass, because we can have biomass that can be exported into the mangroves. How we can measure this several compartments? It's very hard, in fact. The most used is the acid leachable fraction, and this way of measure the metals in sediments take into account the free ions, the complex ions, and one part of the absorbed of the metals on solids. And these methods have some drawback. The advantage is that it's easy and rapid, but the drawback is that you make some desorption or decomplexation by using this extraction. Mostly you have some destruction or some destruction of the carbonates, and it's difficult to predict what happens if you change the condition. It's only a parameter that you can correlate to biological effect index, like low effect range, that can be used what content of metal in a sediment before to have damage in the biota. As an example, we have here the content for copper and nickels in sediments. Okay, it's not really the good way to investigate the relation between organic matter and metals. Another technique is to use the DGT. DGT are very interesting because technically it's the technique that allows to measure only the free metal ions. I don't know if you know this technique, but in fact it's a thin diffusive film. Thin diffusive film. You have a resin and you have a gel here and the filter, and only the free metal can reach the resin. So technically is the nearest technique from the biodisponibility. So because we can consider that the gel and filter act as the cell wall. It's a high sensitive technique, but also it's sensitive to temperature and diffusion. So you need to measure on the same time in situ the temperature and the diffusion and make some calculus to extrapolate the concentration of metal that were seen by the DGT. And also in sediments from mangrove, it's perhaps not the most appropriate techniques, because you need a long time of exposition. So generally it's around 1 week, and it's not able to take into account all the change that can occur during a tidal variation. So you have something average or something integrated, but it's difficult to deduce what can happen inside the sediment. The last way to have the speciation between organic matter and metals is the model, in fact, modeling the system. You need to have a lot of information. It's very hard work to have. But in fact, if you have all the association constant and the concentration, you can predict, as on the right graph, you can predict the speciation of your metal, and also you can predict this speciation under change, temperature, pH, or redox. The only problem of this is if all the inorganic ligands are generally well known, even the adsorption on solid, etc., etc., the less known parameters in this system is the interaction with organic matter. Generally, it is assumed by researchers that we have two pools of organic matter, geopolymers. They don't take into account biopolymers generally. And these two pools are tuned to fit with the experiment. There is no reality. In fact, it's just parameter that you fit to have the good results. But there is some way to obtain some information about the organic matter pool property of complexation. And it's why I will talk about to you now. I took an example from an experiment we done in New Caledonia. We measure or we samples during 24 hours water that come out from the sediments, okay, just on the output of the sediments. You can see here the salinity in red and the pH on the system. And from these samples, we made some experiment of quenching. What is quenching? In fact, it's a way to investigate the interaction of metal with organic matter. The principle is this: organic matter has fluorescent property and the quantum yield of fluorescence. And when this organic matter associates with metals, the quantum yield of fluorescence is decreasing. So if you consider that there is an equilibrium between organic matter and metals, this is the constant or quasi-thermodynamic constant here, and that there is a number of sites of complexation, you can deduce or you can fit these two parameters, number of sites and constant of complexation. You made it by adding little by little the metal. And by adding the metal, you have a decrease of fluorescence. And by using the model, you have an equation, in fact. And this equation, once it's fitted, gives you the constant and the capacity of complexation, which is the number of sites by gram of carbon. So we made this on the 24 samples. We modeled this. Before modeling, we separate the signal. We obtain on the 24 samples two types of fluorescence. This fluorescence was humic-like fluorescence, representing more or less organic matter from our geopolymers, and another here, which is protein-like. During the tidal events, we have here the variation of this concentration or contribution. You can see that for the protein in red, there is no variation or a little. But for the organic matter, the humic-like systems, we had some very high variation of concentration, in fact. And we investigate these samples by fluorescence quenching. So some events occurs generally when there is a variation or just before or just after the variation of salinity. So we think that it's because we have a change of condition in the sediment and there is some activation of biota or protein, not protein, but bacteria, and there is production of organic matters. We will investigate what is the property of complexation of this organic matter. Here, it is the results. On the left, you have the constant, thermodynamic constant, which is the strength of complexation of this organic matter. In blue, it is the humic-like. No, it's not. We consider that there is two sites. In fact, we obtain this. There is two sites of complexation on the organic matter, one in blue and one in red, and it corresponds to two pools of fluorescent organic matter that react with metals. For the constant, we observe that during the middle of the experiment, which is high tide during the night, we have a higher complexation strength. It's not linear, it's logarithmic. It means that during this period, we have organic matter that is 100 times more complexant than the usual organic matter. And concerning the number of sites, meaning that the number of function of complexation, there is also an increase here in the middle and a little bit in the when there is a low tide. But what we can use is that for each samples, we can predict or we can measure what's happened for the metals. So on the same sample, we also measure the total dissolved nickel. So we have the variation of nickels during the tidal event. And we used this complexation data and the concentration of all major calcium, cation, anions, etc. in the water, the pH, and we calculate the speciation of nickel in the water, in this water. This is the results of this calculus. You can see on the left the percentage of organic nickel, meaning the quantity of nickels that is associated to organic matter. We don't know which organic matter. We know only its fluorescent property and its quantity of carbon. We don't know if it is humic substance. We don't know if it is biopolymers. But in fact, it means that this pool of organic matter complex the nickels. And you can observe that during the high tides, there is until 70% of nickel that is complexed. And it corresponds to the lower quantity of nickel in the water. So this means that during this high tide, we have the production or apparition of organic matter that complex more the nickel in the system. And the rest of the time, it's 0 to 10%. So there is a reaction of the mangroves to the system, and when there is less nickel, it complex more nickel. And this type of work was also done by Tayada, for example, and they use more work to calculate also the flux of exportation of metals associated to organic matter. On the graph on the right, you have here in the blue zone the mangroves, nips and prim, and you have the exportation balance of copper and arsenic and also chromium, I think, yes, here. Yes. So what we observe is that on this work, there is an association of the exportation of metal and exportation of organic matter, in fact. Okay, so as we saw before, the organic matter can be highly associated to the metals by complexing property. And if you look at this value, it means that concerning the inorganic sediment or the sediment compartment, there is an exportation of metals. So the mangrove, in the point of view of sediments and organic matter and dissolved metals, act as a source of metals. And I try to make some, well, it's not the same work, but I try to make a comparison between the exportation of biomass for the copper, because it's the similar metal. For the copper, we have retention of a small amount of copper, 0.002 mole by hectare by year. But for the water and the tidal in and out, we have in fact more copper that go out. It's about 0.115 mole by hectare by year. And if we consider this exportation, it means that considering sediments and biomass, there is an exportation of copper. If we look at the stock of metals inside these sediments, it means that by hectare we have a very large amount of copper, and we have time. We have time to eliminate the copper in the mangrove, because it would take most that 30,000 years for this. But what I retain about this small comparison is that mangrove perhaps don't act as only a sink of metallic contamination, but can also act as a reactor that transforms the metals and allow them to be exported in another form, and particularly complex one. And okay, the organic matter is associated to metals, and we have some complexing property, and these complexing property are associated to organic matter, pH, etc., etc. What's happened when I will finish my presentation on the change that suffered the mangroves? You can see here urban ones. You see from Gabon some deforestation, and we have here some consequence of the shrimp production. What we know is that urban impact inputs more labile organic matter. These nutrients active the bacteria at the surface, and even if it is shrimp inputs or urban water inputs, this organic matter with increase the transformation or the mineralization of organic matter, and there will be, yes, less carbon in soils, but also less organic matter that can complex or stabilize the metals. This can be seen here for the two mangroves in Brazil. One is the mangroves of Rio Coco, and the other is from the Pacoti. The first is urban, and the other is quite pristine or less impacted. And this is the constant made on the zone during 6 months, and we can see that more or less it is the same strength of complexation between organic matter and metals. Here the metals is copper. So it means that from cocoa and from Pacoti, there is the same strength of complexation. But if we look at the capacity of complexation, meaning that the number of sites, we can see that in the cocoa there is less than in Pacoti comparing to the global system. Here is the before the mangrove and after the mangrove. This means that during the mangroves of urban mangrove, you have destruction or diminution of the capacity of the organic matter to complex metals. And urban mangroves are the zone where there is more metals. So there is a vicious circle, because you have more inputs. These inputs destroy the organic matter, and this destruction of organic matter release the metals. And also, when with the global change, global climate change, we have also more oxic, anoxic alternance. And with this alternance, we have more erosion and more oxygen. And so there is, again, transformation of the solids phase. And also, well, for the pyrites, you have the liberation of acids, but you have also, for the organic matter, this destruction. And this destruction leads to liberation of metals, because the metal was associated to organic matter. And these metals can go back on the neoform solids, but most of it go because it can be free or associated to organic matter. And this can be seen on another work made by Gopal. After extreme events, the exportation of metals is in front of the mangroves. This is the concentration of cobalt and nickels in front of on the surface sediments in front of mangroves. So there is the extreme event, or the extreme event cause, in fact, the liberation of metallic contamination. And also, to finish, you can have the increase of temperature. We can imagine that increasing the temperature, we can have increase of plants, and increase of plants is increase of organic matter, and increasing organic matter is more exudate, more complexation. But in fact, no, it was shown that increasing organic matter or increasing biomass increase the labile organic matter, and this enhances, in fact, the mineralization at the surface, and it liberates more metals than trap. So increasing CO2 in temperature is not good. Also, it's a vicious circle. It will liberate more contamination in metals. So to finish, because it's time, for me, the organic matter in mangrove, so we show that there is a big affinity with clay and refractory. It is refractory in depth, but fresh organic matter that arrived in the mangroves enhance the respiration and has a bad effect on the carbon stock and enhance the production of the mineralization and production of CO2. And also, it reduces the capacity of mangroves to stop or to complex the metals, in fact, because it exposes the refractory organic matter or the complexing organic matter to degradation or to mineralization. So what we can conclude on this is that mangroves are very sensitive to climate change and human use because of modifying the organic matter in the system that is linked to the speciation of metals. And for metals, we have to constrain a little bit more the reservoir, because if you consider only biomass, it's a thing. But if you consider also the flux and reflux of water in the mangrove, it's not really clear that it is a sink. It can be a source also. And this behavior of mangrove is highly correlated to the property of organic matter to complex metals. As we can see, so that there is it can be 70% of organic matter metals associated to organic matter, and once again, depending on the relation of this organic matter and metals, you can have release due to the disparition or to the degradation of the retention by complexation. As a perspective, I think that we need more investigation on the liability or resilience of organic matter in mangrove, and it is really important for me to know how many amounts of organic matter will resist to the oxidation and the effect of this oxidation on metal release, because this destruction of organic matter or this mineralization organic matter make the mangrove lose their buffer property toward metals. And also in metal stocks, because I tried to find some data in stocks of metals in mangrove, and it's not so easy to have. But if we consider that 1 to 7% of mangrove is lost by year, it means that all these metals and carbon that are in the sediment will be released, but they are not released in the form in sediment. They will be oxidized. And what is the behavior of the organic matter that will be transformed or mineralized toward the metals? We saw that is not really good news, because the organic matter will release the metals. So I think that it's better, or in perspective, we need to understanding the real impact of the global climate change on the mangroves. Okay, I hope that I was not too spread in my presentation, but thank you for your attention, and I'm ready for any question or any remarks that you can have.
Thank you very much, Stéphane. That was an excellent and thorough overview of the geochemistry of mangrove systems. So as always, we open it now to questions, and you can either use the chat function to type out a question, or please feel free to open your mic and your camera and ask the question in person, whichever you prefer.
What is the chat? I try to find the chat. Okay.
So far we have no questions there, but I'll read them out if we do get questions there. Maybe while people are thinking of questions, I could ask you one, and this is about your nickel experiment.
Yeah.
I guess I find it surprising how like the rapidity of change, or the time frame of change, excuse me, in terms of the complexation. Presumably the actual organic matter itself is not changing that much over one tidal cycle. So something must be happening to the organic matter itself. And do you think it's just changes in the binding sites because you've got all the chloride and whatnot coming in as the salt from the tidal intrusion comes in? Or do you think that something in that cycle is actually changing the conformation of the organic matter? You know, some people talk about or like a humic molecule sort of folding and unfolding depending on the chemistry.
Yeah, I think it's the two. When I made the calculation, I take in account all the change in the concentration of cation and anion. So there is the effect of the chlorides, but I think that the change is not really a change of organic matter, but more different organic matter. It's interesting to see that when you have the intrusion of seawater into the sediment by interstitial water, you have like a flash of fluorescence of protein. You have a reactivation of the system because it's not the same water that entering in. And this inside the sediment, this front of new water, in fact, active some biological processes, and there is, for me, there is production. And as you can see on the, perhaps I can share now. In fact, there is also a change in fluorescence, and so it means that it's not really the same organic matter. What is difficult to know is the amount of this new organic matter, because if we took fluorescence, if you have something that fluoresces a lot, it will take a big part of the signal, but is not really a big amount in quantity. So I think that there is a change, not in the river. In the river, it's difficult. In the canal, it's difficult to have a change because you have a big pool of organic matter that come from the river. And if there is some little change, it will be dilute in the system. So it's difficult or hard to see. But if you take, as we have done, just at the output of the mangrove, and we have another site where we observed something like what is the term? A release of very saline water. It happens, and in this very saline water, the organic matter is completely different. It's because probably that, well, in fact, mangrove are reactors. So when it comes on the river, it's difficult to see. But if you take the sample just before or just after the system, you can see this difference and this dynamic. What it could be interesting is to use high resolution mass spectroscopy to see what happened during the cycle, in fact. Because obviously there is transformation.
Okay, thank you. I agree. I think some high resolution characterization would be very interesting on some of those samples.
But it's difficult to have because you have to stay in the mangrove during the night.
Yes.
And also we have had the chance to have the automatic samplers, but we put them really near the front of the sediment and the river. So we have had the chance to have this part of sampling. But to make it for high resolution mass spectroscopy, I think that we need more investigation on more materials to have it in high frequency. Because also you need a lot of matter. This is also the problem. You need a big amount of organic matter for the high mass. This is the fluorescence has this advantage that you need a very few quantity of organic matter.
Yeah, I can see that. Okay, other questions for Stéphane?
Everybody understand all perfectly.
Or maybe it's
Do
just
not hesitate.
good morning.
I saw that there is a lot of people from Gabon, so thank you for to be here. Do not hesitate,
Exactly.
even in French or in Portuguese.
Mhm. Well, it looks like
Okay.
your talk, which I would agree with, it was very, very clear, and everyone seems to have understood it. So one more chance for questions for Stéphane. I would remind you that these presentations are shown on our website. You can go back and
Yeah.
pull it up again. And I believe at the first your email address was on the slide, was it, Stéphane?
Yes. My
Um,
address, I can put it on the chat if you want.
that would be helpful in case people have questions they would like to get in touch with
Yeah.
you privately.
It could be associated to the video if you want.
Yes, exactly. And we know that there are some people who were not able to join us today just because of the day change, and so it'd be good for them to have your address in
Yeah,
the
I
recorded
put it
version
in the
as well.
chat. Ah, sorry, it lost. It it missed the arrobas. Ah, sorry. This one.
Okay. Yeah. Yes. The second one. Okay. Great. Well then, if there are last chance, as I said, for questions, but if there are no other questions, I would just like to thank you again, Stéphane, for an excellent presentation. And I
Thank
want
you,
to
Julie.
excuse me, and I want to remind everyone that we have another talk next week on Wednesday, back to our regular Wednesdays. And it will be Dr. Raymond Ward who will be coming back again. And he's going to be talking on carbon accumulation and sediment accretion, blue carbon, greenhouse gases, and climate change next week. So I hope you'll join us all. You will all join us at that time next week. Thanks again, Stéphane.
Thank you for your invitation.
Yeah,
Thank you
thank
to
you,
all for
Steph.
your attention.